In this video, I'd like to look at applications of Extrema. So in this section, you're going to be given word problems, and so on here, it's extremely important that we know within the word problems what we want to look for. So the first thing you're going to do is read your problem carefully several times, if necessary. Sometimes also we want to sketch a diagram and label. We want to next decide what variable must be optimized. So this will be what we're trying to find the maximum or the minimum for. We're going to write an equation that relates the variables to other information. And then we're going to go through, find critical points. We know if we're going to find absolute extrema, they're going to occur at either critical numbers or endpoints. If the domain is closed, and I'll explain when we get to problems what that means, we're going to evaluate the function at the endpoints and the critical numbers. And then we'll be able to find an optimal solution from this information. If it's not closed, then we're going to verify that our critical value is actually the absolute max or min by using the second derivative test. This will generally be what happens for us for most of our problems. So the idea here is to find a function that we're going to want to take the derivative of to find its absolute max or min. And then most of the time for these particular applications, the absolute max or min occurs at a critical value. We have to make sure that we use the second derivative test to verify that it's the desired max or min. All right, so on here, let's jump into a problem. This one says that a rectangular corral of 32 square yards is to be fenced off and then divided by a stone fence into two sections. The outer fence costs $10 per yard, while the special dividing fence costs $20 per yard. Find the dimensions of the corral that minimizes the cost. And then also find the cost of the least expensive fence. So somewhere within the problem, they're always going to tell you what you're trying to maximize or minimize. So you're ultimately trying to minimize cost in this particular situation. All right. So we've read the problem carefully. We've done that. And then we're going to sketch a diagram and label. So I'm going to kind of put steps 1 and 2 here together. All right, so it looks like we're looking at a rectangle. So I'm going to go ahead and draw me a rectangle here. It says that we want to divide this rectangle into two pieces. It says it's divided with a stone fence into two sections. It wouldn't make a difference here if we divided it horizontally or vertically. There's not enough information in the problem to determine that. I don't believe it said we're dividing it equally, so I'm going to make an attempt here. These are my stones. I'm going to say kind of a bad artist, but I'm kind of trying to here just make a distinction between the straight fence and the stone fence. So there we go. And then I'm going to label. Notice here that we're going to need at least two variables. We'll need a variable, let's say x, for this particular length. If that's x, this is x as well, and so is this over here. And then what I'm going to do here is say that this entire length here is going to be y. Obviously, if that's y, then so is this. I'm also going to make a note that both x and y are greater than 0. So if we have that x or y is 0, then we're not going to have a rectangle. We definitely can't have negative numbers. All right. And then from here, let's go on to step number 3. It says decide which variables must be optimized and then write an equation that relates the variables. So in this particular one, it's actually not the variables x and y here that needs to be optimized, but a cost variable. And so what we ultimately want to try to do is write a cost function. All right, on here, there's always going to be, in step 3, what we call a primary equation and a secondary equation. The primary equation I generally get from whatever drawing that we've done. So we notice here that my primary equation has x's and y's in it. In the problem, they gave us that the corral is going to be 32 square yards. And so what I'm going to do is use that information and the variables that I've been given to create a primary equation. So think of it this way as area. We know that area is equal to length times width. In this situation, they've given us that the area needs to be 32 square yards. My length, let's say here is y. My width is x. Now, what we do with this particular equation eventually is we use it to write one variable in terms of the other. We generally solve this equation for y. Not always, but that's generally what we do. Okay, I'm going to leave a little bit of space here, and then I'm going to go on to what we call the secondary equation. The secondary equation is always the thing that you're trying to maximize or minimize. We're trying to minimize the cost. And so on this one, what we're going to do is we're going to call it our cost function. So I'm going to use C and then equals, and then try to figure out here how to come up with that function. So it says that my outer fence costs $10 per yard. Okay, so what I'm going to do first on it is start by looking at the sides that are outer. So we notice obviously there's a side out here that's outer and there's a side here that's outer. Well, if we add those two sides together to get that length, it's 2y. So we could say 2y, and then how much does that fence cost? $10. And then also add in, we notice also we're going to have a couple of x's here. So we've got x on either side. There, that's the straight fence, so we're going to have 2 x's. That also costs $10. And then finally, we have the interior fence. That's this part here. I'm going to go ahead and just draw a green line there. That one is only 1x, but it costs $20. Okay, so there's going to be how you come up with your cost function. All right, now, what we'd like is we'd like this equation in terms of only one variable. Notice that there's more x's in this particular function than there are y's. So what I'm going to do is come up here, and with my primary equation, I'm going to solve this equation for y. Notice there, if we solve, we'd be dividing out the x. So we have y equals 32 over x, and we're going to substitute this expression in for the y down below. That's the purpose of my primary equation, is so that I can get my secondary equation, which is the thing I'm trying to maximize or minimize, in terms of only one variable. So at this point, we're going to write it C equals 2 times 32 over x times 10. Here, I'm going to go ahead and multiply the 2 times the 10, so that'll be 20x. And then there, we had, what, an x times a 20, so that's also 20x. All right, and then coming down below, let's multiply our constants here in this first group of stuff. So we have there our 2 times our 32, that would be 64, and then 64 times 10 would be 640. That'll be all over x. And then over here with the 20x and the 20x, we can combine those, so that would be 40x. All right, so at this point, what we have is we have the function that we want to try to minimize. All right, so step number 4 says now take and find the critical points or critical numbers. So now with step 4, I'm going to bring that around here. We want to find the derivative of that function. Okay, to find the derivative, I'm first going to rewrite this function in a way that would be easier to take a derivative of. Notice that the x is in the denominator here, so I'm going to rewrite this as 640x to the negative 1, and then the 40x is fine, but I'm going to kind of set that up so it's easy to take a derivative of. All right, so coming back over here, I'm going to say C prime is going to equal negative 640x to the negative 2, and then plus 40. All right, then from here, I need to be able to set this up so I can find a critical number. I'm going to drop this negative exponent down to the bottom, so negative 640 over x squared plus, and then at this point I need a common denominator between these two fractions. I'm going to put this 40 over 1, and then to get a common denominator I'd multiply by x squared over x squared. So that's going to give me negative 640 over x squared plus 40 x squared over x squared. And then getting this together, we're going to end up with negative 640 plus 40 x squared all over x squared. So because I had two separate fractions and I know that I'm going on eventually to find critical numbers, it's important that I get the fractions together as one big single fraction so that I can set the numerator of this equal to 0 and the denominator of it equal to 0. All right, so finding where c prime is equal to 0, that's going to be where the top is 0. So negative 640 plus 40x squared equals to 0. Let's see there if we can rearrange this a little bit. I'm going to add the 640 over, so I'll have 40x squared equals 640. I can divide out the 40. I think that actually goes evenly. So we're going to have x squared equals, that ends up being 16. And then if I take a square root of both sides, that's going to result in x is equal to either plus or minus 4. Now in this one, we don't have what's called a closed interval. The only restrictions that we really have at this particular point is that my x and my y both have to be strictly greater than 0. We already discussed that it couldn't actually be equal to 0 or else a rectangle is not formed. So this is a problem where we don't have a closed domain. So that being the case, we just want to make sure that this x is bigger than 0. So that's going to take out the negative case. So x equals to 4 is the only one that's bigger than 0. So we're going to take out the negative situation. All right. Also, we need to find where the derivative is undefined. The derivative here would be undefined if the bottom were 0. Well, x squared equals 0 is only true if x is 0. That's out because it's not strictly greater than 0. Okay, so that one is no go. Now, here's what we have at this particular point. We've gone through and we've found the critical points. The only critical point we have is x equals to 4. This is not a closed domain type of problem. That means that if we're going to have an extrema, it's going to occur at the critical value. Well, the only critical value we have right now is x equals 4. But the one thing I have to make sure that I do in this kind of a question is verify that it's actually what I'm looking for. I'm looking for a minimum. So what I'm going to do is I'm going to use the second derivative test. The second derivative test says that if you find critical numbers and then plug those critical numbers into the second derivative, the concavity will tell you if they're maxes or mins. Okay. So what I'm going to do from this particular point is go on. So number 5 was out. Okay, so we're not doing number 5 because it's not a closed function. So now we're on to number 6. For number 6, I'm going to take a second derivative, and I'm going to take that second derivative from the easiest place. So notice that down below, my first derivative ultimately ended up being a big fraction so that I could find my critical numbers. But for taking second derivative purposes, it's easier for me to use from the first step up here. So the second derivative, I would say here, multiply the negative 2 by the negative 640. So there, that's going to end up being positive 1280. And then it would end up being x to the negative 3. Derivative of 40 is going to be 0. And so this second derivative is 1280 over x to the third. Okay, now c double prime at x equals 4 is going to give me 1280 over 4 cubed. Okay, that right there is a positive number. I don't really care what it is, but it's a positive number. The positive number tells me that we have upward concavity. Upward concavity would tell me that we have a minimum. So x equals 4 produces a minimum. All right, now the last thing we need to do is actually answer the questions here. I may actually have to wrap around on the top of the next page. That's okay. I didn't leave y'all enough room here to work it. But the ultimate question here was find the dimensions that minimize the cost. We know that the x value should be 4. I believe we have enough information up in here. Notice we have this solved for y. That would find our width or length there, depending on how you look at it. And then it wants to know the cost. We have our cost function right here. So we're able to plug that x value that I've got into the cost function to find that. So let's ultimately here, and I'll just do on the top of the next page, answer our question. Okay, so I'm going to put a little arrow down the ultimate answer here. All right, we have x equals 4, and this was in yards. Okay, so we've got that. I'll go ahead and write that out. 4 yards. All right, what does that mean? Y was originally 32 over x, so 32 over 4 would end up being there 8 yards. So we've got 4 yards by 8 yards being the dimensions. And then what is the minimum cost? The minimum cost is C equals, and I'm going to go back up here to where I highlighted the C equals, and into that plug in 4. So 640 divided by 4 plus 40 times 4, and you can just use your calculator on that. That ends up being $320. So the cheapest fence we can do is $320 with the dimensions of 4 yards for the x's and 8 yards for the y's. All right, so now let's go ahead and go on. What I've tried to do in this section is give y'all a variety of questions so that you can see different things. These type of questions are always a little challenging because you're never going to see the same question twice necessarily. So what I try to do is give you the thought process behind each question so that you're able to adjust for whatever the question actually is. All right, this one says we've got an open box. Is going to be made by cutting squares from each corner of a 3-foot by 8-foot piece of cardboard and then folding up the sides. What size square should be cut from each corner in order to produce a box of maximum volume? So notice here they've told us what we want to maximize or minimize. They say we actually want to find a maximum volume. So ultimately we want to come up with a secondary equation that has to do with volume. All right, so this particular one, we've read through the problem and then let's now label. So we're putting steps 1 and 2 together. It says we have a rectangular, we're cutting squares, but we're cutting squares out of a rectangular piece of cardboard. So I'm going to label that first. All right, on here it said the cardboard was 3 foot by 8 foot. So obviously this over here is the 3. And this over here was the 8. All right, now here's what they mean by cutting squares out. We're going to cut squares out of the corners, and they're going to be equal size squares. So whatever size square we cut out of one corner, we cut the same size squares out of each of the other corners. And then those pieces are going to be removed, and then we're going to fold up the sides to form the box. So here's what I'm going to do. I don't know what size squares that I'm going to be cutting out, so I'm going to label these x by x squares. Now, what that's going to allow me to do is then label the length that's left over here. So let me do that in a different color so you can see. So I have this leftover length or width, however you want to think of that there. Okay, what that's going to be is look at the x's you're cutting out. So you're cutting out x's there and there. You're also cutting out x's here and here. That would mean that if this total distance out here was originally 3 foot, I've now removed 2 x's from that. So that would make this new distance on the inside 3 foot minus 2x. All right, then if I look at the same type of situation, but off, let's say over here, I'm going to do this one in black so you can see it. So let's say here we're doing this one. So we've taken x by x out of the right-hand corner already. We'd also be taking x by x out of here. If this original distance was 8 foot from here to here, we now have that the black part would be 8 foot minus 2 x's. So if we think about a box at this point, and I'm a terrible drawer, but I will attempt to do this. If you think about the box, it's now got these folded up corners. The folded up portions are x, I'm going to say feet tall. This long side along here is 8 minus 2x long. And then if we go over and look at, and I'm just going to take this off to the side for a second. If we come over and look at the shorter side, then this is 3 minus 2x. Okay. And like I said, I'm a terrible drawer, so you're going to kind of have to imagine here. But we've got the idea of this box now, and we've got the dimensions for the box. All right, from here, what we want to try to do is come up with a primary and secondary equation. I think on this one, we don't need a primary because we see everything's in terms of x's. If we have things in terms of two variables, we always need a primary equation. But if not, we can a lot of times just skip to a secondary equation. So on this one, I'll put a little note, primary equation not needed because we already have only one variable. So my secondary equation needs to be the thing that I'm trying to maximize or minimize. So here we notice we're trying to maximize the volume, so this needs to be a volume formula. So the volume for a box is length times width times height. So we're going to say V equals, let's say on this one we're letting the length be the 8 minus 2x. The width would then be 3 minus 2x. And the height would end up being just x. All right, so we've got that. Now, to make this as easy as possible for me to take a derivative of and to even find critical numbers, we're going to go and actually multiply this out. So this is the product of three things. I really don't want to have to use a product rule, especially not of three things. So what I'm going to first do is distribute this x inside to one of these groups. Make sure you don't distribute it to both groups. So this will be 3x minus 2x squared. All right, and then I'm going to FOIL that particular piece out. So I'm going to end up with 24x and then minus 16x squared minus 6x squared and then plus 4x cubed. And then I'm going to go ahead and put this in descending order and combine like terms. So I have 4x cubed and then minus, looks like here, 22x squared, and then plus 24x. So I wanted to gear that up to be as pretty as possible for taking a derivative. All right, so from here, we're going to go on to take derivative and do critical numbers. So I'm going to wrap that around over here. So step number 4, remember this was v equals, so we're going to do v prime equals, this will be 12x squared minus, that'll be 44x, and then plus 24. All right, we're going to hope that this will factor. Notice here, to find critical numbers, we're finding where the derivative is either 0 or where the derivative is undefined. The undefined piece is out because it's a polynomial function. So finding where it's 0, all right, let's see if we can factor out as large a number as possible. It looks like for sure a 4 will go into all of those. So that will leave me with a 3x squared minus 11x plus a 6. Let's go ahead and see here if we are able to factor this. So here we're going to kind of have to use a guess and check method. So let's say we do a 3x and an x, that will get the 3x squared at the front. And then let's say we use factors of, let's say 2 and 3. We know that we have to, if we use 2 and 3, we have to put the 2 with 3 that was already there and not vice versa. Otherwise, you've got groups that share something. And then here, I think if we put 2 negatives, that would get the positive 6 at the back. And then if we multiply to double check to see if we can get the 11, we have a negative 2x on the inside and a negative 9x on the outside. That would give us the negative 11. So we're good there. All right, now for critical numbers, the 4 we don't have to worry about because there's no x with it, so it doesn't make sense to set it to 0. Here we have 3x minus 2 equal to 0, and here x minus 3 equal to 0. This one we have 3x equals 2. That's going to get x equals 2/3. And on this one, we're going to get x is equal to 3. Now, the one thing at this point we haven't talked about is we have not talked about any kind of restrictions that we have. So like, is our domain an open or closed type of domain? In this particular situation, what we've got to do is go back and look. Obviously, x It wouldn't make sense for it to be a negative type of thing because it's, I'm going to say, dimensions of the squares that we're cutting out of each corner. So definitely it's got to be bigger than 0. The other thing I want to do is look at it off of the 3-foot dimension, so the smaller dimension. We're noticing here that the x's are the corners that are being cut out here, and if we're looking at it specifically in reference to that 3-foot section, notice that if we make these x's bigger and bigger, then we'd be encroaching on that 3 feet. We'd be taking more and more out of each piece. If we actually made the x's the exact same size and made them fill up, and what I'll do is, I'm going to say kind of do it this way. If we made the x's big enough so that they were equal, do you see it would actually take out the entire side? And that being the case, we'd be dividing the 3 feet in half. Well, we can't physically do that because then we wouldn't have a box left over. We'd have just a, can't think of it as a taco because you're folding the cardboard evenly. So think of it this way. That x can't be any bigger than half of 3. So the x must be bigger than 0 because we're taking a positive amount out of the corners, but it can't be as big as 1.5, which is half of 3. Okay, so at that point, we then don't have a box, we have a taco, basically. So we kind of can get restrictions out of thinking about what I'm doing with the x's as far as taking corners out and say it couldn't be any bigger than the 1.5. It actually can't even equal 1.5. So those are the restrictions we have. That being the case, if we're coming down here and looking, the 3 is out. We can't take a corner of 3 by 3 out of the corners because that's the whole length of that one side. So that one's definitely out. 2/3 we know is 0.6. That's definitely between 0 and 1.5. So we can say that one would be a good critical number. All right, so now what we want to do is we want to go and verify. We've basically said, hey, we don't even have a closed interval here as far as domain's concerned, so we don't have to worry about endpoints. If we're going to have an answer, it's going to happen when x is equal to 2/3. And so on this particular one, we only now have to verify that we actually have a max or min at that 2/3 value. Okay, number 5 is out since we don't have a closed interval. Number 6, then we take a second derivative. And what I'm going to do is take the second derivative from this step here. That would be easy. So that would be 24x minus 44. And then I'm going to evaluate that at specifically x is equal to 2/3. So at 2/3, f double prime would be 24 times 2/3 and then minus 44. Okay. Plugging that in on the calculator, we're going to get negative 28. Negative 28 is less than 0, which is going to mean I have downward concavity, which is going to produce a maximum value. Okay? So we're going to put on here, so x equals 2/3, and at this point I'll go ahead and put the units back on them. I think on this problem we're talking about everything in feet. So x equals 2/3 feet produces a maximum. Okay, on this problem, I think all it asks is it says what size squares should be cut from each corner in order to produce a box of maximum volume. Notice that it didn't ask for the maximum volume, but if it did, we could plug our x's back into the volume function either here or here, and then that would tell us that actual maximum volume. Okay. So on here we'll say x equals 2/3 feet produces a maximum, and that would be okay as far as our final answer is concerned. All right, so now let's go through and look at, like I said, just another application. I'm trying to throw as many applications here at you as you can so you can see examples of each. Okay, this one says, find the dimensions of a box requiring a minimal amount of material that is rectangular with an open top, a volume of 36 cubic feet, and is twice as long as it is wide. Okay, so on this one, notice that we're trying to use a minimal amount of material. Okay, on this one, maybe it's not totally clear on what we're trying to minimize, but we'll talk about that more here when we draw the picture. So on numbers 1 and 2, we've read the problem, now we're drawing it. It says we're drawing a box. I think it has an open top on it. All right, so here, I don't think we have enough information to say if it's a cube, so I'm just going to draw it as a rectangular type of box to be general about it. All right, so what I'm going to do here, I'm going to dot the top so we can see that the top is actually open. Okay. You'll have to forgive my very bad drawing skills. All right, so what I've done here is I've dotted both, I'm going to say dimensions of back corners that we can't see, and then I've also dotted the top so we can see that this is an open type top. Let's go ahead and now assign some variables. So it gives us some information about, looks like the volume, because it says the volume is 36 cubic feet. It also says it's twice as long as it is wide. So what we're going to do there is, let's say that this down here is the width. We're going to label the side we don't know anything about as a variable. Let's call that x. If that's the case, then the length, which would be this front piece, the way I have it drawn, would be twice that. So that would be 2x. All right, now, it didn't tell us anything about the height, so I'm just going to let the height be y for generality. All right, now notice that my x's and my y's represent lengths, and so that being the case, both my x and my y would have to be greater than 0. So this, once again, is not a closed domain type thing. We can't actually have 0 included. All right, for this particular, I'm going to say problem, we do need both a primary and a secondary equation because there's 2 variables involved. So let's go on over here to step number 3. And with a primary, we generally use the information that they've given us. This one is the 36 cubic feet for the volume. So the volume, once again, would be length times width times height. Our volume we know to be 36. Our length here was 2x. Our width was x. Our height was y. Generally speaking, and I think you're safe to do this all the time, we generally solve the primary equation for y. So on this one, we'll say 36 equals 2x squared times y. And then if we solve this for y, we're going to divide out the 2x squared. And so we get y equals, and then there I'm going to go ahead and reduce, so it'll be 18 over x squared. All right, so that will give us something that we hope we can plug back into the secondary equation so that the secondary equation is in terms of only one variable. All right, so let's go ahead and go to that secondary. The secondary equation is the thing we're trying to maximize or minimize. So they want to minimize the amount of material. What does that mean? That means that we want to minimize the surface area. So when they say amount of material, think surface area. All right, now, so on this one, keep in mind that we're really only wanting to cover a couple of surfaces. We're covering, obviously, the bottom surface. We're covering a side surface here and here. We're covering a back surface and ultimately also the front surface. But the one thing we're not covering is we're not covering the top. So the top remains open. Okay, so think of it this way. We've got a base, which is 1, and then 4 sides that we need to cover. So that's going to be a total of 5 sides. All right, so on here, as far as the secondary, we're going to say surface area, and I'm going to use just S for surface area. That'll make it simple to do notation for derivative. All right, we've got an x times a y here that would be a face of this back side here. We've got that one that we want to cover, but there's going to be 2 of those. There's also an x times a y back in there. That will be the same area. So we have 2, I'm going to say faces of x times y I'm going to say surface area. Then we're going to add, we have the base down here. The base down here is a 2x by an x. There's only one of those. So 2x times x. And perhaps I'm going to say to keep this so that I can see what I'm doing, I'm going to put a 1 there in front saying there's one of those that we're doing. All right. And then finally, I'm going to come over and add. We now have a front and a back that's going to be the same. Okay, the front is going to be this part here. All right. It is looks like 2x width by a y height. And we're going to have 2 of those. That one's going to be on the front, and there's also going to be on the back. And so there are 2 faces of 2x times y surface areas. All right, from here I'm going to go ahead and simplify a little bit, and then I'm going to sub in the y's so that I have everything in terms of just x's. I'm going to neaten this up a little bit first. This will be 2xy. This will be 2x squared. And then this over here would be 4xy. And then I take this expression, and anywhere there were y's down in here, I sub in that expression for the y. So that'll be 2x times 18 over x squared, plus this will just stay 2x squared. And then this will be plus 4x, and then this will be 18 over x squared. All right, from that point, we're going to try to simplify and combine. Notice here we have a couple of x's that can be canceled, and then we're going to multiply the 2 and the 8. So there, the 2 and the 8 will give me 36 over x. The 2x squared would just stay. We also have x's over here that could cancel out, and then we're going to be multiplying the 4 times the 18. That'll be 72 over x. On the next step down, we can combine like terms. We notice that the 36 over x and the 72 over x are like terms. That would end up being 108 over x, and then plus 2x squared. Now what we want to try to do is make this as nice as it's going to be for taking a derivative. We notice that the 108 is over x, so we're going to write that as 108x to the negative 1, and then plus 2x squared. All right, so let's hop on over to step 4, which is going to be to find critical numbers that are within the region that we want. So we're going to find s prime. That would end up being negative 108x to the negative 2, and then plus 4x. We want to get rid of the negative exponent, so this would be negative 108 over x squared. And then we will now want to combine these two as fractions so that we can find critical numbers. Common denominator here would be x squared. So this would be negative 108. And I'm going to go ahead and combine these at this point. This would be plus 4x cubed. We now have this is all over common denominator of x squared. All right, for critical numbers, we're going to say where's the derivative 0 and where's the derivative undefined. It's 0 where the top is 0, so negative 108 plus 4x cubed equals 0. It's undefined where the bottom is 0. That would only happen if x were 0. That's out because we said both our x and y's are lengths, that they can't possibly be zeros. All right, here I'm going to add over the 108. Divide out the 4. So we have x cubed equals 27. If we take a cube root, be careful on cube roots, you don't have to put pluses and minuses. So cube root here is going to end up being just 3. 3 is definitely bigger than 0. So we've got a critical number that's within the, I'm going to say, restrictions of our problem. We don't have to worry about endpoints because this is not a closed interval type problem. We said that our x's and y's both had to be bigger than 0. So if there's going to be an answer, it's going to be x is 3, but we have to make sure to verify that by using the second derivative. All right, so I'm going to put over here, this will be step number 5 is out because it's not a closed interval, but this will be step number 6. And so we want to do a second derivative. I'm going to take the second derivative from the easiest place up here, I believe that's here. So coming down, I'm going to zoom out so we can see that. So that would be multiply the -2 by the -108 in this particular case, I believe. So let's go ahead and do that. So that's 216. It's going to be positive, and then it'll be x to the -3, and then plus 4. All right, and then from there, I'm just going to rewrite a little bit. We'll say 216 over x cubed plus 4. And then what I want to consider is I want to consider s double prime specifically at x is equal to 3. So doing that, I would do 216 over 3 cubed plus 4. We notice there everything's positive, so that's greater than 0. That would tell me that we have concaved up, which would indicate to me that we have a minimum. All right, so on here, we're going to go ahead and say, so x equals 3 is going to produce a minimum, which is good. And then let's go ahead and give our final answer here. This one, I believe it said it wanted the dimensions of the box. And so here we want a length, a width, and a height as our final answers. And so on this particular one, I'm going to go ahead and just come up in here and say, here are your dimensions. All right, so for our dimensions, the first thing is, let's say we do the width. On this particular problem, looking up at what would make sense for the width, I would say that would be the x value here. So that would be the thing that we found. So our width would be x, which in this case would be 3. Our units were in feet, so the width is 3 feet. The length, going back up to check to see what would make sense for the length, I believe that would be the 2x along the front side. So 2x, because x was 3, 2x would end up being 6. So there's the length. And then our height is our only thing we have left. The height would be the y value. So that would be y. Up at the top, we notice that we put y equals the 18 over x squared. So in this situation, we would have 18 over 3 squared. 18 over 9 would end up being 2 foot. So we've got our length, our width, and our height there as our final answers. All right, so now let's look. We got one more example to go. This is more in form of, I'm going to say a business application, which is nice for you guys. So this one, it says the revenue in thousands of dollars from selling X units of an item is given by R of X, and then they give you the function there. The first question, it says find the maximum revenue that the company can earn on the sale of this item. So because of the wording, they're wanting maximum revenue. You know you're going to have to use this procedure that we've just used. We're going to make this note. It doesn't say it in the problem, but we're selling X units. Notice that X would need to be greater than 0. So obviously, if we don't sell anything, we're not going to make any money. We can't sell a negative amount of units. Okay, so that's a restriction. We notice this is not a closed interval type problem. All right, so on here, first thing we're going to do is find the derivative. On this one, we don't have to draw a picture. All right, find the derivative here. We'd have -4/3. The 3 is going to be multiplied to the front. This is going to become x squared. We're going to have an 8x here, and then a 140. I can simplify the 3's there, so I get -4x squared plus 8x plus 140. And then from here, we're going to try to find the critical numbers. So where is the derivative equal to 0? Or where is the derivative undefined? Because this is polynomial, that's out. So we're going to set the -4x squared plus 8x plus 140 equal to 0. Notice here we can factor out, I believe, a -4. So that'll give us an x squared minus a 2x, and then this will be -35. And then let's see if we can factor this. So this will be an x and an x. And then factors of 35 that would add or subtract to 2. We could use a 7 and a 5. The 7 would need to be negative, the 5 would be positive to get the negative 2 in the middle. All right, doesn't make sense here because this doesn't have an x with it to set it to 0, so that's out. This one would be x is 7. This one would be x is negative 5. The negative 5's out because it didn't make sense to talk about a negative amount of products. All right, so on here, the only critical number we have is 7. So if there's going to be, I'm going to say an extreme value, it would happen at the 7. So now what we want to do is take a second derivative to verify that the 7 is actually going to be a maximum in this case. So second derivative, and what I'm going to do is take it from here. So that would be negative 8x plus 8. And then I want to evaluate that second derivative specifically at 7. This particular step is extremely important. It may be not quite the most important step that you do, but if you don't do it, we have a major problem. If you don't verify that this actually is a max or is a min, then it could be that you're giving your reader an answer that's not even valid. So it may be that somebody has asked you to do something that you can't even do. And so if you're finding out, this actually doesn't produce a maximum, it produces a minimum, then you go back to that person and say, we can't maximize the revenue in this case. You've given me something that's impossible to do. All right. On this particular one, evaluating there, you get negative 48. We notice here that that is less than 0, which is going to mean I have downward concavity, which means I will indeed have a maximum. Okay, so the x equals 7 is going to produce a maximum. All right. Now, they asked on this one, it says find the maximum revenue. So at this particular point, we know the value that produces the maximum. We now want to just substitute that x value back into the original revenue function. So R of 7 equals, and you can use your calculator on this, all right, so if we evaluate this at 7, you're going to end up getting 718.66, and the 6's are now repeating at this particular point. However, going back up to the beginning of the problem, it says the revenue is actually in thousands of dollars. So what we're going to have to do is multiply our result by 1,000 to get our final answer. So multiplying that by 1,000, you're going to end up with $718,666.67 if we round that to the nearest dollar and cent. All right, and then from here, the last part was how many items must the company sell in order to reach that maximum revenue? And we've already found that. So on that one, we'll say X must be 7 items to get that maximum revenue. All right, y'all let me know if you have any kind of questions.